All right. So now that you've gone to the hard work of defining all of those procedures, let's see the big payoff as we use it to parse arbitrary strings in arbitrary context-free grammars. Here I've got the procedure add to chart that you wrote. We have the procedure closure that you wrote, once again defined using list comprehension. We've got shift, which either returns something or nothing. And we've got reductions, which has a complicated return based on JState in the chart. Way at the top of this file, I've defined a particular grammar. It's that grammar of balanced parentheses. This is just our encoding of start symbol goes to P goes to open parentheses P goes to nothing. And then down here I've got a candidate input, open, open, close, close. That's in the language of the grammar, so I desperately hope that our procedure is going to find that out. Down here, I have the parsing procedure skeleton that I wrote around your code that does the heavy lifting. So one of the first things I do is take all the input tokens and add in a special end of input marker. And that's because sometimes we need to look ahead, for example, for shifting, to see if the input token matches what's there. And I don't want us to walk off the end of a list. So I'm just sort of padding our data structure by one. Here's the chart. It initially starts out totally empty. It's a Python dictionary with nothing in it. And our starting rule is just the first rule in the grammar. That's by total convention. We're going to start with S goes to P. I pre-initialize all of the elements of the chart with the empty list. Remember in that quiz, I let you assume that it would always be a well-defined list, so I'm making that true here. And then our start state just works on this start rule. It uses the same symbol S. There's nothing before the red dot, then we've got the red dot, and then we've got the P, and that started in state 0. And initially, the only thing in our chart is that at chart position 0, we have this starting parsing state. And what we're going to do is be super lazy and write ourselves a bunch of memos in this chart. Over and over again, we're going to consider additional characters in the input and keep using your three procedures of closure, shifting, and reduction until there aren't any more changes. So I is going to range over all of the possible tokens. And then until there are no more changes, we consider every state in the chart. And the state is something like x goes to ab.cd from j. And I just extract those into conveniently named variables by pulling out the 0, 1, 2, and third element of this tuple. And now we're going to go through three options that correspond exactly to the work that you did. If the current state is ab.cd, we could compute the closure. If C is a non-terminal, we look for each grammar rule C goes to PQR, we make a next state, blah, blah, blah. So here we're about to start parsing a C, but C may be something like expression with its own production rules. We want to bring those in. So here's the code that I promised you in the quiz that I would write. Next state is a call to closure. You implemented closure, and then we check to see if there are any changes. In addition to the closure, there's also the possibility that we're going to do shifting. ab.cd, and if the tokens are C, if the next token is C, then we're totally going to shift. Right? So we're looking for parse token C, and the current token is exactly C. If that happens, we are super lucky. We can parse over it and move on to j+1. So here's the code that I promised you in the quiz I would add, and there it is. Finally, there's our third option for computing reductions. This one is the most complicated. If CD is empty, then we go back in time to chart J and bring something from it forward to this current location. You just finished implementing that. And down here, we have the code that I promised I would include in the parser that calls your function reductions. And then we're just going to keep repeating this until nothing changes. Remember that this was in a while true loop, so we're going to loop over and over and over again until there are no changes, and then we break out of the loop. Down here, I have some purely debugging information. This is all just to print out the chart at the end so that we can take a look at it. We wouldn't actually need this if we were doing a parser. This is for explanatory purposes only. And then down here, I've defined the accepting state. We reasoned to this earlier, which is basically the starting state, but with everything to the left of the red dot and nothing to the right of it coming from state 0. If the accepting state is in the chart in position T when there are T tokens, then we parse the string successfully, otherwise we do not. So down here, I'm checking to see what this value is. Is this string in the language of the grammar or not? And we just print that out. And in this particular example, the string is in the language of the grammar, so hopefully that's what we'll see. Well, Our output is quite voluminous. We see chart position 0, doot, 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 chart position 1, chart position 2. In fact, this was our starting state. S goes to dot P from 0. And then we brought in these other two from the closure. Good quiz question to ask yourself is, why do we have this one? S goes to P dot from 0. And my hint is, remember that P can go to nothing. So actually the empty string is accepted by this grammar. But we end up filling in 0, 1, 2, 3, 4. This one actually corresponds to, look ahead, that sort of end of input symbol that we saw there. And eventually we discover that, wow, our string is in the language of this grammar. We're so happy. This is exactly what we wanted. Now, if I were to change this a bit, I've been very minorly devious, and now instead of having balanced parentheses, I have 3 open followed by 1 close. So now I've changed it so that the string shouldn't be in the language of the grammar. We have 3 opens followed by 1 close. I click Run. The chart is actually going to be very similar at the beginning, changing only near the end, possibly a little bit, but now we report that the string is not in the language of the grammar, as expected.